Greetings everyone, my name is Dr. P. Pavan Kumar and I am going to explain your topic of semiconductor laser in the chapter of lasers in the course Advanced Engineering Physics. Now we'll see that. Now the major contents related to semiconductor laser is its introduction, and you'll see the principle in it, construction, working, and the output wavelength from the semiconductor laser, and what are the drawbacks, advantages and applications of this semiconductor laser. Now let's move to the introduction part of this semiconductor laser. Semiconductor laser is also called as diode laser, and it's made with a PN junction diode. And to make this one, we must use direct band gap semiconductors, and they should always be connected under forward bias only. And because we are using a direct band gap semiconductor, because we need a output should be a photons. So that happens only with the direct band gap semiconductors. And the best example for direct band gap semiconductor is a gallium arsenide. Now we will take gallium arsenide is the example for the laser material in case of semiconductor laser. Now let's come to the principle in case of semiconductor laser is electroluminescence. What electroluminescence here is, suppose if I take a PN junction. Now this is a p-type semiconductor and let it be an n-type semiconductor. Here more number of holes are present, here more number of electrons are present, and when you connect this one under forward bias, the holes from p region, electrons from n region come and join here. By this recombination, a photon gets released. And this phenomena is called electroluminescence. We can also call it as recombination of electron and hole, and where this happens in a depletion region, and that is a principle in case of semiconductor laser. Now let's move to the construction of the semiconductor laser. So a semiconductor laser is a simple PN junction. It consists of p-type semiconductor and n-type semiconductor, and this one is a PN junction. In general we call it as a depletion region. And this one is an electrode, and this shaded one is another electrode for n-type. And these two are connected under forward bias. That is, p-type semiconductor is connected to positive terminal and n-type semiconductor is connected to negative terminal here. Now in this semiconductor laser, active medium is a PN junction semiconductor, PN junction or else, and resonant cavity. Generally these semiconductors have a good reflectivity, so no need of additional mirrors. But if you want your laser should have a more intensity, in that case we can use a silvering mechanism or polish this depletion region, one side fully, other side partially. By that you can use that one as a resonant cavity. So in simple, a reflective coating at the depletion region acts as a resonant cavity in this one. And pumping system is a direct pumping mechanism we are using, a simply PN junction connecting under forward bias. This external voltage acts like a pumping system for this semiconductor laser. Now come to the working of this semiconductor laser. This is the energy level diagram. So this part is for the p-type semiconductor and this part is for the n-type semiconductor. So it's a valency band and conduction band for this, and in case of p-type more number of holes are present here, and in case of n-type more number of electrons will be presented in this case. Now whenever we connect in the forward bias and if we go on giving voltage, the holes in the p region they will come to the depletion region, and electrons in n region they will come to this depletion region. As a result, what happened, a hole from p region, electron from n region come and join here, emits a photon. This emits a photon here, and this emitted photon will come and this pushes the another hole towards the junction. And if the photon moves this side, this pushes the electron to the junction here. As a result, one more recombination come into the picture. Something like this acts like a stimulated emission in case of semiconductor laser. So like that, more times more photons will push these electrons and holes towards this depletion region. That leads to more photons gets emitted from this depletion region. So all the recombinations happens in this depletion region, we call that one as a active region. So active region or depletion region, both are same. But in case of laser, we must mention it as active region because all the recombinations takes place in that region only. Now, but what is the wavelength of emitted photon? Now we will see that. So we know all EC minus EV because the electrons move from valency band to conduction band and photons gets released. So we can write EC minus EV is equal to h nu, where nu is the frequency of emitted photon and h is a Planck's constant. EV is the energy of the valency band, I mean highest energy of the valency band, and EC is the lowest energy of the conduction band. Now, nu is a c by lambda, that's a c is the velocity of photon or a light, and lambda is the wavelength. Now substitute nu value here, and another thing, EC minus EV can also be taken as energy gap. Now, by substituting these two things in the previous equation, Eg is equal to hc by lambda we can write. Just rearrange the terms, take lambda this side and energy gap this side. You will get lambda is equal to hc by Eg. Here hc are the constants. So, lambda is inversely proportional to energy gap. Means the output wavelength is purely depends on only on the energy gap of a given semiconductor diode. Now the major drawbacks of the semiconductor laser is very low power compared to other lasers, and the lifespan is less compared to other lasers. But even though the drawbacks are there, there are very good applications with the semiconductor laser, especially the optical fiber communication. That's what Internet on Fiber works on with the help of semiconductor lasers. And generally we do observe the lasers in toys and pointers, pen pointers with the lasers. All these things are made with the semiconductors because of their small size. And the major advantages of the semiconductor lasers are you can get a continuous or pulse laser. If you want continue, you can get it. If you want a pulse laser, you can get it from the semiconductor laser. And its weight is very less and the size is also very small. Because of that, this become more compatible to many applications of this semiconductor laser. So this is about the semiconductor lasers. Thank you very much. Happy learning. Thank you.